first speaker today is Nikita Selinger, who will be speaking about classification of Thurston maps with parabolic orbifolds.
Hi, so first of all, I want to thank Vladimir and all the other organizers who are not here. This is a lovely conference, and I thank you for inviting me, and even more so for giving me an opportunity to speak. I will talk about my joint project with Michael Yampolsky from Toronto. And without further ado, I want to start with giving the main results. So that, well, we're pretty generous here with time scheduling. If I have to stop early, at least we'll have that already. So the topic of the research is Thurston's theorem. So my talk will be somewhat related to what Dimo was talking about yesterday, and I'll reiterate most of what he said. This is, on one hand, this is similar. On the other hand, the agenda is somewhat different. So it all started by talking with Misha Yampolsky. So he, with his co-authors, proved the following result, that if you have a Thurston map with hyperbolic orbifold, you can algorithmically decide whether it's equivalent to a rational map or not. And the argument is very simple, and we'll get to that in a moment. The argument is basically trivial. And then the next natural question would be, if you have two Thurston maps, can you decide if they are equivalent or not? And of course, if you can find a rational map they're both equivalent to, you can then just check if that's the same rational map or not, because that's unique optic conjugation. But, so the hard part is what happens if both of them are not equivalent to a rational map. If both of them are obstructed, then the question is still open. And so I'll report on partial progress towards solving this question. And so I think we're basically there. So there are some parts that are open, but it all boils down to something with solvability issues within mapping class groups, and I'm pretty sure there are people who would know how to do that. We're both not really experts on that, so we just postpone doing that, but I'm sure it's all doable. So main results, and these are sort of meta statements, and I'll try to explain over the course of the lecture what these words actually mean. So first thing is that every Thurston map admits a constructive canonical geometrization, and so basically for those who know what the objects are, I'll say now, and I'll explain later for those who don't. If you have a Thurston map and it's equivalent to a rational map, then this rational map can be thought of as a geometrization of this map. And if it's not, then you can decompose and try to geometrize every piece. And that's what it is. So we're proving that you can do that algorithmically. And then the next theorem, which is a main ingredient in doing that, is that classification theorem for parabolic Thurston maps. Namely that a marked Thurston map with a parabolic orbifold is geometrizable, which means is equivalent to a quotient of an affine map, if and only if it has no degenerate lattice cycles. For most of it. So I'll give precise statements later. This is almost true. So there are some exceptional cases where both can happen. And then the third theorem is exactly that there is an algorithm. This is a partial solution to this comparability problem. There is an algorithm which, for two Thurston maps that have only hyperbolic pieces in their canonical decomposition, can say if they're equivalent or not. So if you decompose and you get other kinds of pieces, it's slightly trickier. So we don't have a result there yet. But as I said, I believe that it should be possible to do. Okay? So those are the main results, and I'll try to explain now what these words actually mean. Okay. So we'll start with Thurston maps. And Dima already described what that is. I'll repeat. So we take a branched rational, something that looks like a rational map on this field. So we take a branched cover. We take a map which is locally a homeomorphism, except at some finitely many points there might be branching, so it will look like z goes to z to the d around the origin complex plane. And for such a map, you can define, well, we define a Thurston map as a pair of such a map and a marked set, P sub f, where this marked set we require to contain all the critical values, so these ramification values, and it should be finite and forward invariant. In particular, this implies that the map must be post-critically finite. So the orbits of all critical values must be finite, because otherwise, of course, there is no such thing. Okay. So in classical theory, in Thurston's work, he actually used PF was always the post-critical set, so the forward images, the forward orbits of critical points. However, it turns out that in many applications, including all the stuff I'll be talking about today, it's important that you allow this flexibility of adding extra points in this marked set. Because that's what happens when you start decomposing a map. If you even start with a map F, PF, where PF is the post-critical set, and it turns out to be obstructed, if you decompose it, you might end up with a map that has extra marked points, which don't come from critical orbits. Okay? So that's the definition of Thurston maps, and two of them are the same up to what's called Thurston equivalence or combinatorial equivalence. So of course two maps from the dynamical point of view would be the same if they're conjugate, but here we require a slightly more flexible condition. So they have to be conjugate on the marked set, and in the complement of the marked set, we only require them to be homotopic to each other. And the theorem, which was proven by Thurston and then first published by Doherty and Hubbard in '93, says that a post-critically finite range cover except 2-2 maps. So there are 4 twos, but I'll say 2-2 because, yeah, I guess that's the extent of my abilities. So, except for 2-2 maps, a Thurston map is either equivalent to a rational map, which then would be unique, or it has a Thurston obstruction. Okay? And I'll define what a Thurston obstruction is in a moment, and what a 2-2 map is a little bit later. So usually in most of my talks, I tend to hide this under the rug. So this except clause, I say it's not important because there are not too many of them. But the whole point of this talk that there are enough of them that it makes sense to study them, and at some point you actually have to study them. And so this exceptional case is the main object here that we're studying. So some definitions, we'll call a closed curve essential if it's not homotopic to a marked point, or if it's not null homotopic. So it has to have at least 2 marked points in each of the complementary component. And a multicurve, so a simple closed curve. And a multicurve is a finite collection of those such that they do not intersect. And again, so from this point on, when I talk about simple closed curves, I'm always talking about them relative to the homotopy with respect to the marked set. So non-intersecting means that they can be made non-intersecting up to homotopy. And we can define F inverse of gamma. Actually, I don't think we will need these definitions, but anyhow, so we can define the F inverse of gamma to be the multicurve of all essential mutually non-homotopic preimages of curves in gamma. So if you have a multicurve, you have a collection of curves, you pull them back by F, you get a different collection of curves. They also will be simple and non-intersecting, just because we require our curves not to go through any critical values, so the preimages will be unbranched. They all will be simple curves. And then you can throw out, so if you have several of them that are homotopic to each other, you throw all out but one. And you end up with a multicurve again. Okay? And a multicurve is called invariant if this preimage of the multicurve is contained in it, and completely invariant if it's actually equal. And now Thurston defined this linear transformation on the space on the foremost space of all multicurves, of all simple closed curves. So if you think about giving weights to every single curve, you can define this linear transformation just by pulling back those weights. And so if you have some weight associated to gamma, if there is a weight associated to gamma, when you pull it back, you take the pre-image and you associate to that pre-image the weight 1 over the degree of the map restricted to that pre-image. Okay. And so this defines this linear operator from this space R to the power of all multicurves, the formal vector space where generators are the simple closed curves. And if you restrict it to a finite dimensional subset, if you take a multicurve and you project this operator to the finite dimensional subset, you get, well, a linear operator on there, which is a matrix, right? And it has, so we call it the Thurston matrix of the multicurve. And by definition, all the entries will be non-negative. They will be sums of these expressions 1 over the degree, and degree is always a positive number. And so the leading eigenvalue of this matrix is also real and non-negative. And a multicurve is a Thurston obstruction if this eigenvalue is at least 1. And the thing is that here in this definition, you don't actually have to require that multicurve be invariant in any kind of sense. It's not important. If it's not invariant, in some sense, it's even worse. Okay.
So, I mean, what are the words you need to say to allow, you don't have an eigenvalue if you're not invariant?
Yes, you do.
You don't even have a linear map from a space to itself.
If you have a linear map from a space to itself, find a dimensional space to itself.
Yeah,
Specifically.
but if you don't have
It has eigenvalues.
If you don't have an invariant multicurve, what is your linear map?
So I take this operator
You know?
and I project the domain and the range onto the sparse of gamma. And I get an operator.
Still the main page is one is
Oh, so you just discard all.
I just discard all the pre-images that are not homotopic to the curves.
Okay.
If there are some.
Okay.
So if it has even more pre-images than the ones that give you this. So this is consistent with the definition of a Levy cycle, because when you define a Levy cycle, you never actually require it to be invariant, which we'll see momentarily.
But you will get it invariant. It's not invariant just by going to bigger space, you get something invariant. Finite dimension.
Well, the same would be the case here. It's a lemma, which you can
Yeah.
prove, but the same would be the case here. So it's exactly in this sense that it's even worse if your thing is not invariant. Then you can find a larger thing which is invariant, it's still an abstraction. This requires a proof, but it's fairly true. Okay? So let me just illustrate for those. I mean, most of us know what this is, but for those who don't, let me just give an illustration of the motivation behind this definition, because if you see it for the first time, it doesn't really make much sense. So the motivation is as follows. Suppose you have a rational map, let's say, and suppose the picture is like that. You have some annulus. So the rational map maps Riemann period itself. So you should think that there's a bulb here and a bulb there, but there is an embedded annulus in the Riemann sphere, A. And suppose it has 3 pre-images, or maybe it has more, but it has 3 pre-images, A1, A2, and A3, which are within itself. Okay? And of course, well, we assume that this annulus A doesn't have any critical values, and therefore these pre-images don't have any critical points, so they are unbranched. So those will be coverings from one annulus to the other of some degrees, D1, D2, and D3. Okay? Then, if this has a modulus something, this annulus will have the modulus of this annulus will be exactly that something divided by D1. And the modulus of that one will be that something divided by D2, and that by D3. And then necessarily, by Grothin equality, the sum of this 1 over di's will be less than 1, because all of these annuli are embedded in the original one. Okay? So if your map were rational and you had a picture like that, then this would hold. And this is, the primitive example, the simplest example of a Thurston matrix. Right? So if you consider the multicurve of exactly this curve, then this is exactly the matrix. The matrix will be 1 by 1 matrix is just one number, and this is exactly the number that you'll get. So a system like that will be an obstruction if and only if the sum is at least 1. Okay? And it's clear that for a rational map it has to be smaller than 1. Well, at least less or equal, but if the picture is exactly like this where they're disjoint, then it's actually smaller. Okay. So this is the motivation. And the general definition basically tells you the same thing, only with more curves. If you take more curves, then each of them can contribute to each other, and then you get this whole matrix. Okay. Yeah, by the way, so feel free to ask any questions. Since we have like at least 20 minutes reserved for questions, you should feel free to ask them at any time.
So you are requiring it. You just said that you weren't going to require levy cycles to be invariant.
Okay, so let's look at the definition.
Yeah.
A levy cycle is a multicurve such that each gamma I, so each next gamma, has a preimage of degree 1, which is homotopic to the previous one. Okay? So this is a levy cycle. It doesn't have to be invariant. It can have some preimage which will be not homotopic to any of those curves.
It's not completely general, it's partially invariant.
Yeah, it's partially invariant. It's not as if you.
Well, what is partially invariant?
Well, I mean, in particular, you have this cyclic.
You have this one pre-image that's...
There's always one pre-image. You don't just arbitrarily stop.
Well, it's not an arbitrary multicurve, I'll give you that, but I don't quite understand what it actually means to be partially
that to
invariant.
me looks quite a strong invariance
Yeah.
property.
For example, what we worry about is you just go out and you choose some random curve and say, well, just keep pulling that back as long as you can, right? And it might just be that one more pullback.
Actually, that's just as bad as, so it's a good question, but if you have an infinite sequence of curves that just pull back without cycling, but that pull back with degree 1 to the next one, that's just as bad as
We could
this
probably
system.
make something invariant out of that, I agree, but...
Well, after the fact. After the fact, you can make something. So again, there's something to prove, but it's just not too hard. But that would be just as bad as this one. But I mean, of course, you do require some property in the definition of a levy cycle. So there is some invariance here, but it doesn't have to be invariant in the sense of the definition I gave before. Okay? So once again, a levy cycle is when every next curve has a preimage that is homotopic to the previous curve. Okay? And a degenerate one is when you can, so these curves have preimages that are homotopic. Gamma 1 has a preimage that is homotopic to gamma naught with degree 1. And the cycle is degenerate if you can actually extend the map in one of the components. So you call one of these components of gamma naught, complementary components of gamma naught, to be interior of gamma naught. And you want the map to be actually homeomorphic on the whole interior of gamma naught. So, another way to think about it is that these curves are collapsible. You can pinch them together, and the dynamics within those curves is in some sense very simple because it's a homeomorphism. Okay? All right, and the theorem that's how this whole project started. The theorem that Yampolsky, Bonneau, and Braverman proved is that there exists an algorithm which for any Thurston map with hyperbolic orbifold outputs either an obstruction or an equivalent rational map. Okay? And the idea is very simple. So you do the two things. You enumerate all possible multicurves. It's a countable set. And it's a lemma, you have to prove it, but you can enumerate that. There is an effective way of enumerating all single closed curves on the surface. And so you take every single multicurve and you start checking if that's an obstruction. And that can be done algorithmically. You just pull it back, you compute the Thurston matrix, then you compute the eigenvalues with enough precision to tell if they are larger than 1 or not. Well, you can check, you can actually check if there is one that is equal to 1, and then you can, for the rest, you don't even need precise values, you can just estimate. You know, this all can be done numerically. I'll be throughout this whole talk, I'll be very vague about what it actually means to be done algorithmically, because that's sort of not the main point of what we're doing. But nevertheless, so this kind of thing can be done numerically. You enumerate every single multigraph and you just start checking if it's an obstruction. And of course it's an infinite process, a priori, because there are countably many of them. But then another thing that you can do, you can make a list of all rational maps that could be possibly equivalent to your map. Right? So if it's equivalent to your map, then you know that the degree is the same. And then you know that it's post-critically finite. And that gives you enough algebraic conditions to find a finite set of possible things. And
finite set of possible rational maps, and then a finite possible set of homeomorphisms as well.
well, the possible homeomorphisms, the set of possible equivalents is actually infinite, because
Yes.
you have to take...
Yes, that's what, well, you're going to tell us about.
So there are only finitely many possible rational maps that could work.
Yeah, I agree.
But so you basically have to check for every element of the mapping class group if that realizes equivalence between two given maps. Well, unless you know how to do it otherwise.
Well, so that's not algorithmic, is it? See, because you must have some way of cutting down to a finite number of homeomorphisms.
So that's the thing. And now the punchline comes. So this is also a countable process. You enumerate every single homeomorphism in the mapping class group, which is basically the same thing as enumerating simple class curves. Well, it's slightly harder, so if you can do one, then you would do the first one. And this gives you another countable process that eventually finds you a rational map. And now you start these two processes at the same time. One of them has to finish in finite time. One of them has to finish in finite time by Thurston's theorem. So each single one of these processes could be infinite. So you do them in parallel, and once one of them stops, you just, ignore the other one. You stop the other one, you say, okay, we're done. So by this process, you either get a multicurve, which is an obstruction, or you get a rational map, which is equivalent to yours. So that's the whole beauty of the argument. It's very soft. So I should make a disclaimer. This has nothing to do with actual doing things on the computer. So if you want to write a program that would do things like that, this is most definitely not the way you would start doing it. And there are much better ways that are based on Thurston's proof of Thurston's theorem, where you start iterating in a Teichner space and you converge. If you converge, you'll converge it at geometric rates, so these algorithms would work pretty well. The other thing is that theoretically it's not easy to prove. It's not easy to theoretically prove that this algorithm actually works, right? So in practice, what you do, you start iterating, and when the next iterate looks just the same as the previous one, then you say, declare this to be a fixed point. But in theory, it's not easy to prove a qualitative result of saying that if you get this epsilon close, then you're definitely done. You can no longer diverge. Okay. So that's why. So what we are doing is pure theoretical things. So we want to prove a theorem, not to actually write a program, because these programs would not work well. Okay? But this is sort of theoretical miracle. You have two infinite processes. You start them at the same time. One of them has to stop by Thursday.
Well, I suppose you could formalize, if you really cared to, you could formalize the statement and even the proof details, for example, in terms of covering spaces and even fundamental groups, where it's like actually kind of a discrete computation.
No, so this is formalized, that this is discrete computation. It's possible to do on the computer. It's just not doctor recommended. There is no reason to do this on the computer. It's possible.
But a priori, you don't know how long it may take to, given the branch code you have, from an algorithmic point of view, you don't know when it will stop, right?
Yes, there is no way to estimate the stopping time. Well, basically it's random
Right.
in some sense. The stopping time of this algorithm is random because it has to do with enumerating all possible things, and then you just start checking them, and it may as well happen. So it can be any particular one on your list that does it for you.
Could you, so I'm missing a subtle point, or maybe I'm missing an obvious point. What is it about Thurston's theorem that says that one of the processes must stop in finite time?
So let's go back to the statement. So Thurston's theorem says that exactly one is true, that either you're a Thurston equivalent to a rational map or you have an obstruction. And you check for both things, so one of them has to be true eventually. Yeah, so your question is exactly right. So basically, if you actually write this program and you start checking for a particular map, it will never finish. It will never finish in our lifetime. So we know that it has to finish, but
If you're lucky, you might just finish.
if you're lucky, you just take the random multicurve and it turns out to be an obstruction.
So it's a consequence of the law of the excluded minimum.
Yeah.
Yes, exactly. And it's kind of amazing that this kind of thing works.
That is magic.
Okay, well, unfortunately, this doesn't exactly translate into comparing two things. Because when you start comparing two things, if both of them are not equivalent to a rational map, then you have to do something else. And the idea of doing something else is to decompose, to use Pilgrim's decomposition. Okay, so this is the conjecture, that there exists an algorithm that can produce a combinatorial equivalence between two Thurston maps, or say that they are not equivalent. This is the goal, which so the main theorem 3 was partial resolution of this conjecture. And I mean, I'm 100% sure that this is true, and I'm 99% sure that with not so much effort, one can promote what we are doing to a full solution of this thing. Okay?
Well, hold on, what the distinction is?
So there you just check if it's equivalent to some rational map.
Oh, here you have two maps.
And here you have two Thurston maps, you want to check if they're the same. So as I said, if one of them is equivalent to a rational map, then the problem is trivial. Because then either the second one is equivalent to the same rational map, or has an obstruction. Or equivalent to another rational map, which is also gives you that it's not equivalent. So in that case, we are done. But if both of them are not equivalent to rational maps, you have to decompose. Well, I mean, maybe you don't have to, but that's the only approach we know.
But isn't that exactly your methods that you develop find a way to, they must decompose in the same way if they're equivalent?
Yes. Well, it's sort of clear that they must decompose in the same way if they're equivalent. That's just from the reality of decomposition. The problem is, the main point is, if you have two decompositions, you want to find decompositions for which you want to be able to say that if they're equivalent, that there's equivalence that sends one decomposition to the other.
The decomposition is essentially unique.
That's very much not true.
Um,
That is not true, and that's the whole problem here. If the decomposition was unique,
You can't use the canonical.
so we are going to use the canonical decomposition, which is unique.
okay. Cool.
But
I would say that's essentially unique.
Yeah, once you.
yes, so the canonical decomposition is unique, but there is plenty of ways to decompose.
I think
Yeah.
it
Well, that
has
just means your proof isn't unique.
No, but the whole point of this discussion is that how do you know which decomposition is canonical and which isn't?
Oh, that's right, there's no, that's right, there's no.
If you say we start with a canonical decomposition, then of course it is unique. But if we start with a Thurston map, how do you find the canonical decomposition? And that's in the heart of the
Or
matter.
maybe you can phrase it, suppose you have a decomposition, how do you see a priori topologically it's canonical without running the Thurston?
Well, that too. That's one part of the problem, but then you have to find it. Well, of course you can, again, run countably many things and check for each one if it's canonical or not, but that's not good enough if you don't have the other counterpart.
But I mean, is there a definition of canonical obstruction that doesn't involve saying, run the Thurston algorithm, run the Thurston pullback algorithm and calculate all these?
So we're getting there. Okay? So you're right, of course, but that's the whole point, the difference between theoretical part and algorithmic part. We need to know which one is canonical, and then, of course, the canonical is unique. Okay? So this is the part that I never have in my talks, but now in this particular talk I have to describe that. So orbifold signature that we attach to a rational map is defined as follows, or more generally to a Thurston map, is defined as follows. You take, for each x, you take the least common multiple of all degrees of all iterates of f that end up in x. And then you define the Euler characteristic of the thing you get as 2 minus this expression, the sum of these expressions over all points. So again, if you've never seen it before, it doesn't make much sense, but let me try to explain it the following way. We have a branched covering on the surface. If we have a covering of that surface, we can, of course, lift the map. So if we have a covering of our sphere, we can lift the map F. The problem is that there aren't really many things that cover the sphere. Since it's simply connected, the only coverings are homeomorphisms. But instead, let's consider branch coverings. Now, branch coverings, you cannot always lift by branch covering. So we'll allow branching points only at the same places where F branches. Okay? And then what happens, actually your map can become better. By doing that, when you lift, not only it lifts, but the branching is consumed by the branching of the covering, and so you get an unbranched map. Okay? So you want to find a minimal surface, a minimal branch covering of the sphere, which will, such that when you lift your map F, it becomes unbranched. Okay? And then you look at what kind of surface you get, and sometimes you get a surface which is Euclidean, and most of the time you don't. So the Euler characteristic of this surface will be either 0 or negative. It's an easy lemma that it cannot be positive. And so either your surface is a Euclidean surface, and there are only 3 of them, I believe. So it's either the plane, the cylinder, or the torus, or it's a hyperbolic. Okay? And so if you stare at this formula, so you have 2 minus the sum. These things are always.
Okay.
So these things are 1 minus something. This something can be 0 if v of f is infinite. So we allow this least common multiple can be infinite if you have a point which is in the critical cycle, because then when you keep coming back to it, the degree of the map keeps growing and growing and growing exponentially. So if it's infinity, then you get 1 here, and if it's not infinity, well, the least thing that you can have here, which is not 1, is 2. So that's another miracle that we always use, right? So, natural numbers are very much discrete. So if it's larger than 1, it's at least 2. And then, so this thing, if it's not 0, it's at least 1/2. Which means that there could be, if this is 0, there could be at most 4 points for which this function v of sub f is non-zero. And then you can just list all the possibilities. So you get infinity, infinity, 2 to infinity, and so on. And the most important one, the most interesting one is 2 to 2 to 2. So if you notice, so the way I stated Thurston's theorem, here I said just accept 2 to 2 maps. And the original proof was accept all maps with parabolic orbifolds, and also it was about maps, so the marked set was only allowed to be the post-critical set. But in this generality, it was proved, for example, in the manuscript of Tunley Tsui and Roof, I believe, and it's actually the same proof.
So with the extra points.
With the extra points, and the proof actually works just as well for all parabolic maps except the 2 to 2 maps. Okay. And there isn't much to change in the proof. The only subtle detail is that when you prove the definite construction part, you need to go to higher iter than 2. But that's the extent of it. All the other arguments work, just as in the original proof. I also have a proof of that in my papers, which is, again, it's essentially the same thing. So if you're rewriting a proof of Thurston's theorem, you may just as well include it, but it's not really a big deal. So we're mostly interested in these 2 to 2 maps. And the picture of this 2 to 2 map is easy to understand in some sense. So it's a map that can be lifted to a map of a torus, a self-map of a torus. And that self-map on the torus will be unbranched. Okay? So the orbifold, you can think of this sphere with this orbifold structure as the pillowcase orbifold, which is, you take R2 and you divide it by the action of this group. So first you divide by the action of the usual torus fundamental group, so by the action of Z, Z2. You get a torus, so you get a fundamental domain which is a square, and then you fold this square, you cut off half of it, and you fold the other thing, and you get a pillowcase. So that's exactly what it looks like. If you look at a pillowcase, it has 4 corners, where the total angle is only 90 degrees? 180 degrees. 180 degrees. And all the other points are flat. All the other points are flat. This actually, you can observe that. So when you take a pillowcase and try to iron it, you can iron flat any point except at the 4 corners. Even the points that are usually at the crease, if you move around and you start ironing them, that becomes completely flat. But you can't really do that with the quarters. Okay? So you get this map on the torus. You can think about it this way. You have a map on the torus, and you just quotient it by this endomorphism, by the involution of the torus, or by the involution z goes to negative z. And you get a map which is defined on this pillowcase. And every map on the torus, so it's an unbranched map, so it's a covering map from a torus onto itself. The lift of F will be a covering map of the torus onto itself. And that, of course, acts on the homology of the torus. And homology of the torus is Z2, so you can think of this map. It has an inherent integer matrix associated to it, which will be important in the later discussion. Okay? So if you don't add extra marked points, if you only have these 4 corners as marked points, when you lift up, these marked points disappear, and the only invariant that you get is that matrix. So you get that 2 maps are equivalent if and only if those matrices are conjugate. Okay. So in that sense, the classification is very easy. But if you start adding marked points, of course, you have to care what lifts of those marked points do on the torus. Right? So our main result is the classification of these 2 to 2 maps. And it's very similar to the classification to the Thurston statement. The difference is that, you see, you get this matrix, the action on cohomology, the action on homology of your map, and if that matrix has different eigenvalues, different in absolute value, this never can be equivalent to a complex map, because complex matrices would correspond to complex conjugate eigenvalues that are the same in absolute value. Okay? So it's not a right notion. If you think about it this way, you take your favorite map, like you take a matrix 2, 1, 1, 1. You act on it on the torus, and then you quotient down to get an action on the pillowcase. That can never be conformal. That can never be equivalent to conformal because it stretches one direction by one factor and stretches another direction by another factor. Probably you should take 3, 1, 1, 1 so that the determinant is larger than 1. But the idea is that, right? So you shouldn't compare these 2-2-2 maps to rational maps because they don't have to be holomorphic, they don't have to be conformal. So instead we compare them to affine maps. And the statement is that F will be equivalent to an affine map in most cases, unless it admits a degenerate Levy cycle, so unless there is an obstruction to that. And that affine map is essentially unique. So this is a statement which is completely analogous to the statement of Thurston's theorem, but this is the statement for 2-2-2 maps. And actually for all maps with parabolic orbifolds, you can make the same statement. So the thing is that the maps with other parabolic orbifolds, the first 5 signatures, can be incorporated in both approaches. So they can be viewed as, since these will all give rise to matrices that do have same eigenvalues, same absolute value eigenvalues, and therefore, because this thing will have more symmetry, and therefore they will always give you conformal affine maps.
How much choice is there? You have only 3 post-critical points in those.
Yes.
The Teichmüller space, isn't that just a single point?
Well, if you don't add extra mark points, then it is, yes, then
Yes.
there is nothing to prove. But now suppose you mark, so this is the typical question this theorem wants to answer. You take a map, like you take a Chebyshev polynomial, it's z squared minus 2, and you mark a periodic cycle. There are plenty of periodic cycles. You take your favorite one, you mark it. Then you take 2 points of that periodic cycle, take any curve, your favorite curve that connects them, and day twist around it. Take small neighborhood and do a day twist there. What do you get? Do you get a map which will be equivalent to the one you started with? So will it just amount to relabeling the marked set? Will it be something, well, I mean, it can't be really something different. It either will be the same map only with relabeling, because after all, we know that the map sort of stays the same. Or maybe it becomes obstructed. That could happen. So this is exactly the kind of questions we want to answer by this theory. If there are no marked points, then there is a unique map. Okay? In the first 3 cases. And in this case, as I said, the unique invariant is the matrix. You can compare them by just, you compute the action on homology of one thing, you compute the action of homology on the other thing. You check if those things are conjugate as integer matrices, which is very much algorithmically solvable. Compute eigenvalues if you want to just check. Okay? But if you start adding mark points, the question becomes non-trivial. Especially, so, and it's non-trivial, but in these cases it can be treated exactly the same way as in the case of hyperbolic orbifolds by some miracle. And in this case it really cannot. So that's the main effort and the main subject here. Okay? Any other questions? All right. Yeah, so the corollary would be, the immediate corollary would be that if you apply this algorithm by Braverman, Bonawani, and Polsky to the parabolic case, there exists an algorithm that for a 2-2 map either produces an affine map, which is conjugate to a quotient of an affine map, or it outputs a degenerate Levy set. And you do exactly the same thing, you just start looking for one or for the other. If it is equivalent to a quotient of an affine map, you know which affine map to take. You just compute the matrix, and you take that affine map, and then you try all possible equivalences. And again, you just enumerate all multicurves and look if one of them gives you a Levy cycle. Okay? So it's the same kind of problem. All right, so now I want to discuss the Pilgrim's decomposition theory. Okay, and this is exactly the case where a picture is worth 1,000 words. And there are even more words in Kenneth's book. But it can all be very well understood just by looking at the picture. So suppose you have the following thing. You take, yeah, so maybe you can't really see that. I can barely see that. But there are also bulbs coming out of these tubes. I don't know why they're different color. Okay, so those are spheres. So these tubes also connect to the end spheres. Sorry about that.
Phantom spheres.
Hmm?
Phantom spheres.
Yeah, phantom spheres. Well, you can kind of see them. Well, at least I can kind of see them. Probably not so much for you. Anyhow, so suppose you have the following thing. You have, in the picture, you decompose it into thick and thin components. So you have these bulbs connected by tubes. And basically this is an arbitrary decomposition a priori, but what you want, the property that you're looking for is that when you pull back this picture, if you pull back all of these curves that separate different components, you get another picture like this, and then you recover the same structure. So you get all these curves that you had before, and then all the other curves, all the other preimages of these things will be either inside of those tubes, or they will be trivial, so inessential in the sense of definition I gave before. So they will be in the thick components, but they will not surround any points, or maybe at most one. Okay? So if you have a system of annuli like that, you call this a decomposition of your map. Okay? And for any invariant multicurve, you can do this thing. Right? Again, so invariant, everything here is defined up to homotopy. So having an invariant multicurve is enough for you to construct a decomposition like that. And it's a decomposition in the following sense. So now every thick component, every bulb is mapped into the other bulb, and you can iterate that. And there are finitely many bulbs, so every bulb is pre-periodic. And the most interesting ones are the ones that are actually periodic. So for a periodic one, you can define a first return map. And it will be a first return map of this bulb, though of course it will have holes in it, but you can patch every hole by a disk. You just patch it up, and you get a branch covering defined again on a sphere. So this will be a decomposition piece. So you get a new Thurston map, or in some cases a homeomorphism, because degree can drop, and sometimes it drops to 1, so you get a homeomorphism. So you either get a homeomorphism or a Thurston map on a marked sphere. Again, so you can think about this as some kind of renormalization procedure if you wish.
On the bulbs, what about the thin parts? What's happening there?
Well, on the thin parts, we know what's going on. Like if you take a preimage of a thin part, it's always in some degree covering. So that information is recorded by the Thurston matrix of the curve we start from.
I mean, the annuli map over one annulus would map over a union of annuli and bulbs, right, in general. And
Yes, but that's not the way we want to look at this picture. This is very much correct. But the way we want to think about it, if you take a preimage of the thing, then it's strictly within, well, there are several components, but each component is strictly within an annulus.
Yeah, okay.
So the other picture is is much more difficult to understand. If you take this thing and start mapping it, it will cover some annuli, it will cover some thick parts, it can cover the whole thing and do that. So that becomes messy. But going in the opposite direction is easy. Okay? But now for every periodic bubble, you define this renormalization of your map. You define the first return of your map to that bubble, and that's a new Thurston map or a homeomorphism. Okay? And that Thurston map, as I said, even if you start with a map with no extra mark points, this Thurston map that you get in the decomposition may very well have extra mark points. So you have to do it in this generality. It's not only that it comes for free, so we want to write a general statement, but you actually have to do it because that comes out in applications. That also comes out in some other applications, like when you do matings. If you want to prove that some pictures of matings actually converge to what they do, because you see that they converge, right? Some people can actually produce computer pictures and you see that they're very well convergent, but you can actually mathematically prove that they converge to what you see using this kind of theory. Okay? And now there comes the question from Adam. So this is the theorem, this is actually part of my thesis, that there is a purely topological description of canonical obstructions. So for those of you who don't know what a canonical obstruction, you can just take it as a definition, because it's sort of not really related to the rest of what I'm talking about, so I'm not going to define it. But for those of you who do know, a canonical obstruction has the following topological properties. So this topological property of canonical obstruction is the Pilgrim conjecture. So this theorem is stronger than the Pilgrim conjecture, but the main part is to prove Pilgrim's conjecture.
So
Well, there is something more
the
to it.
conjecture essentially yielded a topological description, or?
With some more effort, yes. But once you know how to prove one, the other parts are easier to prove. Okay? They do not follow, but they're easier to prove. So when you develop enough tools to prove one, you're in a good position to prove the rest of the theory. Okay? So when you decompose along this canonical obstruction, what happens is that the decomposition pieces no longer have canonical obstructions. For each decomposition piece, the canonical obstruction will be in. Which sort of means different things for maps with hyperbolic and parabolic orbifolds, because for hyperbolic orbifolds that immediately implies that there are no other obstructions. But for parabolic orbifolds there might be other obstructions, but they're also easy to classify. So you see, for example, if you start with a fine stretch, you take the matrix n0, 0, n, you just stretch everything n times, you get a map of degree n squared on the torus. And it projects to a very well-defined and conformal map, flexible lattice example on the sphere. But that does have obstructions. Because if you take a curve, any curve basically, it will have n preimages of degree 1 over n, and the matrix will be 1.
What does the F star have against the Thurston matrix, or?
So F star, this is the action of this lift on the
Is the
homology
half
on the torus.
restriction?
So this is the matrix. So for 2, 2, 2 maps, there is this associated matrix.
So what is the hat?
So you lift it to the F to the torus,
Okay.
and then there is the action on homology, which is a matrix.
And for the second part, you mean no Thurston restriction of F on the restriction of the first return part of F?
Yeah, so the restriction, the first return map is a Thurston map which has no Thurston obstruction.
Right.
Okay? If it's a not a 2, 2, 2 map, there are no other obstructions. And in this case, there are no canonical ones in the same sense, but there might be the ones that I just described. Basically, they are the only case. Okay? So if this matrix has an integer eigenvector, if this matrix has two eigenvalues that are equal and integer, then there must be Thurston obstructions just from this action on the homology. But they do not spoil the rest of the picture. Okay? So this is a complete topological.
Now, I just wanted to wait for it. We said there exists no Thurston obstruction in F. That must mean there exists no Thurston obstruction of.
So F capital is a first return map in the cycles. So you start.
Oh.
So this is not F small, which is not even in the theory.
So the little f is what you start with.
Yeah, you start with a little f, which is
Okay, sorry.
which is here, right? So you start with a little f, and capital F is the renormalization. Okay? So this part of the theorem was, well, a slightly weaker statement was conjectured by Kevin in his book, and I proved it in my thesis, and then I went on and proved this statement. Okay? So in this sense, we do have a topological description of canonical obstructions, and that's very important for what we are doing, because we want to construct canonical obstructions. So this is the next statement, that there actually exists an algorithm where Thurston map can produce the canonical obstruction. Okay? And now we can use that decomposition, which is unique. So that's exactly the point of doing this. Well, it's a nice statement in its own right, but it has its applications. Okay? And this is the outline of the argument. So you run the algorithm from Yampolsky and co-authors to get an obstruction of gamma. Well, you might just prove that there are no obstructions, it's equivalent to a rational map, well, in which case you're done. Okay? Then you decompose along that obstruction that you already got. And then you get profit. So you check the conditions of that previous theorem. And if they are satisfied, you go to the next step. And if they're not satisfied, that means that you can take one of those cycles of components and find a further obstruction within there. Then you add it to what you already had. That forms you a larger multicurve, which is an obstruction, and you keep doing that. And of course, at some point you've got to stop because a multicurve cannot have more than, well, whatever the amount of mark points minus 3 you have. Okay? So you end up with a maximal obstruction. Oh, well, you don't have to end up with a maximal obstruction actually, but you end up with an obstruction that does satisfy the conditions of the previous theorem. Okay? And we say that the canonical obstruction is the unique minimal one which satisfies those things. So once you've found one of them that satisfies those things, the only thing you have to do is you take all of its subsets and you check for which of them these are satisfied and which are not. And you take the intersection of all of those for which it's satisfied, and that gives you the canonical obstruction. Okay? So this is only possible because of this theorem and the fact that we can do this BBY algorithm not only for hyperbolic things, but also for parabolic things. If we decompose and we get a parabolic thing, it's not that bad because we can keep doing the same thing. Okay? Until we prove that this parabolic thing doesn't have any obstructions within there. Okay? Alright, so let me remind you, this is the copy of the first slide. So this is what we did. This is essentially this analog of Thurston's theorem for parabolic maps. And this is what basically this theorem implies immediately. That now what you can do is you take your map, you either find its geometrization in the sense you find an equivalent rational or an affine map. And if that doesn't work, you find the canonical obstruction, you decompose, and then you geometrize every piece. So in this sense, you canonically geometrize every Thurston map. Okay? And then the next theorem, which also follows, well,
Wait, could you go back to that last step? Once you have found maximal, so if you check the conditions, if you find a maximal obstruction, oh I see, not every maximal obstruction, if it fails you just discard it, but then you have to start again to find another obstruction, right?
no, so what you do is you find an obstruction.
Yeah.
You check if it satisfies the conditions of the theorem.
You find that maximal obstruction. Okay.
Well, actually, I want to take it back. We don't need to find a maximal obstruction. So let me explain it once again in words. You take an obstruction. If it satisfies the condition of the theorem, you go to step 4. If it doesn't, that means that there is a larger obstruction which contains it. You take that, you check. And you keep doing that. So you take larger and larger obstructions until you find one that satisfies the conditions of the theorem. If you found the maximal one, any maximal obstruction has to satisfy the conditions of those theorems.
Okay.
Okay? You don't have to. You don't have to end up at actually the maximal one, but if you end up at a maximal one, that necessarily does satisfy the assumptions of the theorem. And then once you found one that satisfies the assumptions of the theorem, it's enough just to check all of its subsets, which is a finite thing. Okay? And this yields this result. So if we know that all decomposition pieces are hyperbolic, then we can check if these are the same. So we check piece by piece if the corresponding pieces are the same in the decomposition. And if they are the same, then for hyperbolic maps, the Thurston equivalence is unique. So if the pieces are the same, then there's a unique map from every piece to every single piece, and the only thing that we're left with is to patch those pieces into the global map. Okay? So let me maybe go to the picture, this picture. So if you know how to, if there is an equivalence between if you have two pictures like that, decompositions of maps F and G, you know that pieces must map to pieces. Well, of course there is like a permutation of pieces, but that's finite information. So you can check for all possible permutations. But now if you know that this piece maps to that piece, you compare their rational maps that they're equivalent to. And if they are the same, there's a unique way to define equivalence on this piece. So this way, there is a unique way to define equivalence on all thick components. You define it first on all periodic ones, and then you pull it back to all pre-periodic ones. And the only freedom that you have left is to define your equivalence, possible equivalence, on the annuli. And it turns out that on the annuli, this becomes a linear problem, because the amount of mapping class group that you have left after you fix everything on the thick parts is just z to the power of the number of components. And it's very easy to solve problems in abelian groups. So basically, this will amount to solving a linear equation. You can form a linear equation, and if it has an integer solution, then that produces you an equivalence. And if it doesn't, then there is no equivalence. Okay. So in this way, we can prove this third theorem, which is a partial resolution of the main conjecture in the stuff. And I'm pretty sure that for a person knowledgeable enough in the theory of mapping class groups and solvability questions in mapping class group, you can promote this. So the question becomes more difficult if you have other kind of pieces, because the equivalence is no longer unique. And so you get a whole subgroup of equivalences.
Well, you mean the non-hyperbolic pieces?
Non-hyperbolic pieces. Then you have this whole subgroup you want to check. You sort of have to, a priori, you have to check for every possible element of this subgroup if that gives you a decent result, but that's an infinite choice. And you want to reduce it to the finite choice. But it's not as simple as in the case of a abelian group, but I think it should be doable. Okay? So I can stop now, or I have another slide to give some idea of the probability. Well, you can ask me a question. I'll stop.
So we have 15 minutes. Does anyone have any questions?
I would like to see some ideas of the proof, if possible.
Okay, so very, thank you for your kind question. Very briefly. So this is what actually becomes very useful. We had to adopt Nielsen's theory, which is a very classical thing, to our setting. So we're talking about endomorphisms, not homeomorphism. So Nielsen theory originally was designed to work with automorphisms, with homeomorphism of surfaces, and there it's easier. But it turns out that our 2-to-2 maps are they're basically the next best thing. So they're not too complicated, and you can define something which is analogous, completely analogous to Nielsen theory. So you define a Nielsen index by the following. So if you have a periodic point, we know that our map F, the 2-to-2 map F, is covered by the map on the torus, which you can further lift to map on the plane. And that map on the plane will be, you can prove it, it's an easy lemma. That map on the plane is affine on all the integer points. Just by the virtue of lifting. It will be affine on all the integer points and even all the half-integer points.
What do you mean a universal cover? You mean a lift to the universal cover?
Yes. By a universal cover of a map, I mean you lift it to the universal cover of the thing.
Like the universal cover of the orbifold?
Yes. So that's what I'm saying. You can take There is the orbifold universal cover, which is you can lift the action of your map to a map on the whole Euclidean plane. And because it's a lift of a map on the orbifold, it will automatically be affine on all the privileges of the corner points, which are all integer points and all half-integer points. Okay. But in the complement of those points, it can do anything. The only restriction is that it's G equivariant. Right? Okay.
What's the orbifold group?
So the orbifold group is all integer translations plus, well, it's generated by all integer translations plus z goes to minus z. So it contains all integer translations and all symmetries with respect to all integer points. Okay? So that is the orbifold group for the pillowcase. So we're talking only about 2-to-2 maps. So there is only one orbifold we're talking about, which is quotient of the whole plane by this particular group. Okay?
So
The group G.
it's like an orbifold analog of the vector transformation.
Yes, exactly. This is universal covering in the sense of orbifold. And the depth transformation group is the orbifold group G, which is a very explicit group.
Nice and small.
Hmm?
Nice and small.
Yes. Exactly. And so we can define for any periodic point, if you have a periodic point, when you lift it, that means that when you iterate, when you come back to the same point downstairs, that means that you moved by some depth transformation element upstairs. Okay? And this depth transformation element we will call the Nielsen index of the periodic point. And of course that depends on the number of iterates you take and on the lift. Okay? So this is the definition of Nielsen index. This index is an element of our group. And it's well defined for every point, unless it's a point which is projected to one of the corner points, because for those points, there is a depth transformation which fixes that point, which is the symmetry with respect to that point. And so it's defined up to that symmetry. And so you can say that 2 points are in the same Nielsen class if there is a universal cover for which both of these points are fixed. Or if the points are periodic, then you take a universal cover and you take its nth iterate, and you want nth iterate to be fixed simultaneously. So if that can happen, the points are in the same Nielsen class. And it turns out, of course, these definitions are related. The points are in the same Nielsen class if and only if they have the same index for any particular choice of the lift. So for this particular choice of the lift, they will have index, which is the trivial element of the group by definition. But then if you take any other lift, they still have the same index. Okay? And then you prove the following statements, that you have a degenerate Levy cycle if and only if there exist at least 2 different points, marked points with the same Nielsen index. And the same Nielsen class.
Just take the arc joining.
Yeah, so basically, one direction is that if they have the same Nielsen class, you can choose an arc join in them which will be invariant. Because they're both fixed, and you take a preimage, you get essentially the same arc. Okay? That's the idea of the argument. It's not extremely hard. And, well, the other direction is a little more involved, but also.
So remember, what is degenerate Levy cycle again means what?
Degenerate means that one of the component is also mapped by homeomorphism, of the complementary component. Not only the curve is mapped 1-to-1,
Right.
but it can be filled in one of the components to map 1-to-1.
Once we collapse the point with a
Yeah.
loss of map.
Yeah, so in our case, if you have a Levy cycle, for 2-to-2 map, basically if you have a Levy cycle, it must be degenerate. Unless you have a very specific 2-to-2 map where one of the eigenvalues is equal to plus or minus 1. And this is sort of an excluded case from all of this discussion, because all of the statements I'm telling are not true for that map. That map is kind of weird.
You've
Okay.
hidden this from us up to now?
Hmm?
You've hidden this from us up to now, that there's one more exception?
Well, it was written on the statement. I never said it out loud. It was written in the statements, somewhere hidden, like, yeah, such that the associated matrix is hyperbolic. So it's such that the associated matrix doesn't have eigenvalues plus or minus 1 in this particular case. Okay, so that's the first part that you prove. And then, yeah, so, yeah, I guess that's what I just said. And though, if you know that all points have different Nielsen indices, then you basically know where your conjugacy should map them. When you try to conjugate it to an actual affine map, that tells you where to map them, because for an affine map, you can define Nielsen indexes for an affine map, and for each Nielsen index, to get the corresponding point, you just solve a linear equation. And if you assume that your affine map doesn't have eigenvalues plus or minus 1, the solution will be negative. You just solve a linear equation, you check the determinant is non-zero, then there's a unique solution. It's 2 by 2 matrices. It's not terribly hard. And so you sort of know already where to map all of your marked set. And then another step of the proof, which I can't describe in too much detail, is that you basically show that no matter what you do with the rest of the things, you get the same, you get the map in the same equivalence class. So it must be equivalent to the affine. Okay. So those are sort of vaguely, very vaguely ideas of how one proves the classification of parabolic. Okay. Any other questions?
There are no other questions, let's thank the speaker again.